In this lesson, we are going to introduce autocorrelation of a time series, but we are going to introduce it with a familiar approach, which is the approach you use when you study correlation between two variables in the introductory statistics class. So we will use an app to review correlation between two variables, as it's usually done with random samples in an introductory statistics class. That is, random samples are data that have rows that are not correlated. And it's the typical type of data that you use in most of your statistics classes. So we apply the concept of correlation to calculate the correlation between a time series and the lagged time series obtained from that time series, and we will call that autocorrelation at lag k. And then we'll show how R gives us similar information as what we do with the sample autocorrelation function of a TS object. And we'll mention some differences between what we do and what the ACF is doing. And we'll also discuss why and when to use the ACF. The ACF is really the most important summary statistics of a time series. So why do we need to know all this? Well, autocorrelation in a time series is expected and is one of the most important features of the random term of a time series. Different autocorrelation structures are indication of different stochastic processes. And we get from that a hint as to what the model is going to be for the data, the model for the stochastic process. Autocorrelation also, on the other hand, is not an intuitive concept for beginners that have been trained with independent, identically distributed observation kind of data. So that's why I use a technique that is familiar when learning in the introductory statistics class to introduce the concept of correlation in between time series and lagged values of the time series. So if you don't remember if you don't remember correlation as you learn it in your introductory statistics class, you are invited to view my demonstration of it in this app. What this app is producing is the values of this coefficient, which is called the sample correlation coefficient, and is denoted by little r. The autocorrelation coefficients that we're going to calculate from a time series also are going to be called little r, but they will have a subscript k because we will have several correlations. We have the autocorrelation on lag 1, autocorrelation on lag 2, autocorrelation on lag 3, and so on. So we'll have many correlation coefficients where for a time series like this, for example, the correlation coefficient is calculated with this formula, and it's actually similar in concept, at least, to what we are going to do with time series and the lag values of the time series. So in a separate video, I demonstrate the app and I discuss further the interpretation of correlation between two variables. So please watch that separate video, which is just a demo of this app. We continue now, assuming that you have watched that video before the rest of this lesson. So we're going to start now the lesson with the Johnson time series data that we used in the prerequisite lecture. And remember that we formed this new data set from just the JJ time series. The Johnson time series is quarterly data, and we put together this data set in the prerequisite lecture using just this time series. Second column is just the lagged at k equal 1. So this is correlation R sub 1. This will be, if we calculate the correlation between YT and YT minus 1, that will be R sub 1. Correlation between YT and YT minus 2 is R sub 2. Between the correlation between the column YT and YT minus 3 will be R sub 3. And correlation between YT and YT minus 4 column will be little r sub 4. So the idea is that those correlation coefficients that we learn to calculate between two variables in the introductory statistics class can be used to calculate correlations between pairs of variables. Okay, in this strange constructed data set that we put together in the prerequisite lecture. So the data set that we put together in the prerequisite lecture was on purpose made look like a data set with 5 variables. And then we know how to calculate the correlation for a data set like this between 2 variables. So we are going to do that. So recall that this is just a screenshot of the first rows of the data. There are many more observations in that data set. If you run the R code that is posted separately, you will be able to see that. So with this familiar data set, then we can do what we do with data sets like this, check the pairwise correlations between the variables. So a typical thing that we do in introductory statistics class is the pairs plot. The pairs plot tell us the scatter plot pairwise, right? And so, for example, this is scatter plot here at the top is showing the relation between the Johnson-Johnson time series and the Johnson-Johnson time series lagged a lag 1, right? Lagged 1 value, applying the backshift operator to it once. And then the correlation between the Johnson-Johnson time series and the Johnson-Johnson lagged 2 quarters, right, is this other plot here, the second plot on the top. The correlation between the Johnson-Johnson time series and the lagged version of itself at lag 3, applying the backshift operator, b to the 3rd power, is given by this 3rd plot. And the correlation with of yt minus 4, is given by this plot on the top. The other plots are showing the correlations between pairwise correlations between the different lagged versions of the time series, right? And so they also play a role, but for now we'll be concentrating on the top ones because those are the ones that we first look at in a time series. So basically this is pairs plot is giving us correlations between yt minus 1 at the top, yt minus 2, yt minus 3, and the yt minus 4 column. And we can also calculate the numbers, right? So the numbers, again, that are interesting are the ones at the top of the correlation matrix. This correlation matrix in the top has that correlation of yt with itself is 1, and obviously that's the case, right? Correlation of the Johnson-Johnson time series and itself lagged 1 value, 1 period, right? 1 quarter is 0.943. Correlation between Johnson-Johnson and itself lagged 2 quarters is 0.955. So that would be yt and yt minus 2. Correlation between yt and yt minus 3 is 0.939. And correlation between yt and the column yt minus 4 is 0.995. And that is calculated using that coefficient that we showed in the previous slide. Okay, so let's go back. We are using this correlation coefficient, this one. So using the same correlation as we will do for a data set like this, pairwise, we calculate the correlations between the different lag values of the lag versions of the time series and the original time series. So in introductory statistics, right, when we have a data set like this, we calculate correlations between variables, between the columns. Calculating autocorrelations is a similar idea, but it's because we are doing now the correlations, the familiar correlations between yt and yt minus 1, yt and yt minus 2. These are not called correlations anymore, but autocorrelations, because indeed the data that we have in column yt is data that is producing the data in yt minus 1 and producing the data in column yt minus 2, right? So it's really correlation of the time series with itself, but at different lags. Okay, that's the idea. Now, there is a function in R called the autocorrelation function, which is also a summary statistic, the most important summary statistic of a time series, that gives us the same information as the autocorrelation matrix and plots the correlations in this plot. Usually we'll do more than 4 lags. Okay, with the Johnson-Johnson, we just calculated the version of the time series on lag 4, up to lag 4, but we could do up to lag 25. And that's what the autocorrelation function gives us. This ACF is a function that tells us the same information as the first row of these pairs matrix and the first row of the correlation matrix. But for many more like versions, notice that we would have had a very large pairs matrix and a very large correlation matrix if we had calculated the Johnson-Johnson like versions up to 25. We would have 26 columns, right? A data set with 26 columns. So it's not worth doing all that because you get the idea, right? With just a few lags. But that's what we're doing. What we are doing is for this data set, right? Notice that this plot is representing the correlation at this at lag. I'll explain what these numbers on the x-axis mean. Is the value of this correlation on the vertical axis. So this vertical lines is just giving us indication of what the value of the correlation in the first row of the correlation matrix are, and in these plots, right? So for this one, right, the second plot on the top of the pairs matrix is the same, is representing the same thing, the correlation that is represented by the value at the top of this line, vertical line. The red one, right, is the third correlation, 0.939, but it's not going to be 0.939, so I'll just qualify that in a little bit, but it's this representing the relation represented in this pair plot, okay? YT minus 3 is represented by the height of the fourth vertical line. And then the correlation between YT and YT minus 4, which is represented by the last scatter plot on the top row, is going to be the height of the fifth vertical line here, as represented in the y-axis. So there is a correspondence between the first row of the correlation matrix, the first row of the pairs matrix, and the values of the first, second, third, fourth, and fifth row heights of these lines. Okay, so let me explain now what the values that we got there in the autocorrelation function in this new plot are. Notice that the first autocorrelation is 1, because that's the autocorrelation at lag 0. We say it's the autocorrelation of the time series with itself. And ACF by default gives you that autocorrelation. So that one you can ignore, the first one, but then at lag 0. And the others, notice that the correlation of YT minus 1 in the ACF is 0.925, which is a little different from the correlation between YT and YT minus 1 in the correlation matrix. And why is that? The numbers that follow the correlation in the ACF between YT and YT minus 1 is 0.888, and it is 0.955 with the way we did it. Now, don't forget that when we did these autocorrelations in these scatter plots, we were using the complete cases. On the other hand, the autocorrelation function uses the as much data as possible to calculate these autocorrelations. Okay, so let's look at that idea in the next slide. This is originally, if you go back to the pre-requisite lecture, how the data that we created looked like when we liked the Johnson-Johnson. When we created YT, right? When we created YT minus 1, which is JJ.B, of course, we started at quarter two, YT minus 1 is 0.71, is the observation in the time before. Right? At quarter 3, YT minus 1 is the observation of the time series at quarter 2, and so on. So we are gradually losing more and more values here. We're creating more and more missing observations. But notice that if we calculate the correlation between YT and YT minus 1, we could start at quarter 2, right? Whereas the correlation between YT and YT minus 2, we will have to start at quarter 3. because the others are missing, right? With a correlation between YT and YT minus 3, we could start at quarter 4. And the correlation between YT and YT minus 4, we could start at quarter 4. Quarter 1 of the next year. So we could use more observations to calculate the first autocorrelation and the second autocorrelation and the third autocorrelation than when we had the complete case. Okay, so that's the difference. That's why these numbers obtained with the ACF are different. There is also another difference with how we calculated the Pearson correlation coefficient. Okay, and that comes from the formula of the autocorrelation coefficient. The autocorrelation of a time series with itself lagged k periods is this formula. So notice how we are calculating the top of this ratio, the numerator, is different from the numerator in the Pearson correlation coefficient. And the denominator is also different from the Pearson correlation coefficient. In the autocorrelation formula, which is this formula, we just divide by the sum of using the whole time series t equal 1 to n of YT minus the sample mean of the time series. Okay, so we are always using the whole complete number of observations. On the other hand, on the top, we are reducing the number of observations as the number of as the lag, as the k increases. Okay, so that's the difference, and that's why the numbers are slightly different. But the idea is the same. The idea is that we are calculating correlations between columns in a data set where the columns now for the time series are just the same time series but lagged 1 period for YT minus 1, lag 2 periods for YT minus 2, lag 3 periods for YT minus 3, lag 4 periods for YT minus 4, and so on. And the ACF is going to summarize all that information with the height of the vertical lines representing the correlations between YT with the other columns. Okay. Now in the x-axis, notice R produces something that says 0 to 1, 2, 3, 4, 5, 6. Remember that a TS object in R is looking at the time series as something that has a frequency, a certain number of observations per year. So 1 represents a year, 2 represents a year, 3 represents a year, right? Third year, fourth year, fifth year, sixth year. And within a year, you have four observations because the Johnson is quarterly. And therefore, you're going to have 4 autocorrelations. R1, R2, R3, R4. R1 represents correlation YT minus 1, R2 YT correlation YT minus 2, R3 correlation between YT minus 3, R4 correlation between YT and column YT minus 4. And that's what you need to have clear. The representation by the software is always something that needs to be clear, because one thing is the math, one thing is the representation in terms of data, another one is the summary statistic itself. So you need to understand what the summary statistic represents. All right. So now the question is, well, when do we do this operation of calculating correlations between YT and the columns representing the lag values of YT? Well, it does not make much sense to study the ACF of a data set that has a strong trend, like the Johnson. You saw that all the autocorrelations are really high. All the R sub Ks, R1, R2, R3 are super high because of the trend. So we don't learn anything new. We already see that the data are correlated because of the trend. Okay, so it usually it is usually not used for the data in its trend form. And also, if there is seasonality, that is going to also show very prominently in the autocorrelation function. If once you remove the trend, of course, and once you get rid of the trend. But again, we already see the seasonality. It is a feature that we, excuse me, we don't need to learn more about. It's clear. from just looking at the plot. So again, it's gonna not give much information. So the interesting ACF is the ACF of the random term. And remember, in the decomposition lessons, we learned how to decompose a time series. For a reason, we want to study the random term, and the ACF of the random term is what will make sense. So there was correlation in what we saw between a time series and lag versions of itself, the columns representing the lag version, and we call that autocorrelation. Because there was a strong trend upwards, the correlations are very high. So we don't learn much new about the data by doing ACF of a trended data set. And we also know that correlations with complete cases differ slightly from those given by the sample ACF, because the ACF uses as much data as possible, and also because the formula for the autocorrelation is different from the Pearson correlation coefficient. Okay, and it's reassuring to see that we do not need to do all the work that this lesson used to demonstrate the concept of autocorrelation, because once understood, we can just use the ACF function in R to apply to the time series or transformations of it and find the correlations really quickly. So I hope you enjoyed this introduction to autocorrelation, and we'll see much more about autocorrelations throughout a whole time series course. And I just stop here for now and stop this recording.